Okay, chemists, we're going to wrap up the solutions unit and talk about what are called colligative properties, which are things that depend on the amount of solute particles, but not the actual identity of the solute. These are things like freezing point changes and boiling point changes, and if we're talking about that, that means we should look at a plot of pressure versus temperature and look at a phase diagram. Remember how a phase diagram works? It separates your regions of solid and liquid and gas for a given substance, and this might be what waters looks like. And if we pick some point arbitrarily, let's say 1 atmosphere, to be right here on the y-axis, where that line crosses the solid-liquid line and the liquid-gas line correspond to, respectively, the freezing point and the boiling point, TF and TB. Well, remember what we said in the last lesson is that solutions will have a lower vapor pressure. Solutions have lower vapor pressure, P-vape. So compared to a pure solvent like water, the solution is going to have a line that separates these phases that falls below where we see these splits. So we'll have some line that looks like this for salt water and this for salt water or sugar water or anything else with a non-volatile solute. So this is for our solution. Which means if we look at where it hits those lines, now our 1 atmosphere line is hitting a different point on the x-axis, and we actually have a higher boiling point. And if you go back to the solid liquid line, it actually hits the x-axis at a lower freezing point. And that's a very brief breakdown about what we see with boiling point and freezing point. Solutions will boil at a hotter temperature and freeze at a lower temperature, which really just means it wants to stay in the liquid phase, and you can actually use an entropy argument to explain that there's a favorability in mixing the mixture into a liquid. It's actually a separation technique when you boil something because the gas and the liquid separate from each other. And likewise, it's a separation when you freeze something because the solid is freezing out of the liquid. So it's more favorable due to entropy to stay in the liquid phase, but this phase diagram just shows us a little bit about why those points are higher. Now what's the point? Well, we can quantify this. We can quantify this lower freezing point and higher boiling point with an equation that lets us measure the change in temperature. It's actually the same equation for each of these. It's delta T is equal to a term that's abbreviated I times a constant K times the molality M. And I'm going to write the same exact equation for both and then highlight the differences. The freezing point depression is just delta TF and the boiling point elevation is delta TB. I'm going to put absolute value signs outside of them because that will remind me that delta TF is always a lower freezing point and delta TB is always higher, so we're really just concerned with the absolute value here. M is the molality. I'm just going to label that up here. We learned that in the first lesson of solutions. K is a constant. It goes with what the solvent is. Happens to be 1.86 degrees Celsius per molal for water. It's different for boiling. It's 0.512 degrees Celsius per molal for water. And I'm going to denote those as Kf and Kb, respectively, just to point out that they're different. So the last thing to talk about is this I. What's this I factor? That's called the Van't Hoff factor. And the Van't Hoff factor is essentially the number of particles. And what do I mean by that? Well, that's how many particles you get in solution for a given solute. So for example, let's say I have sodium chloride. Sodium chloride dissociates into a sodium ion and a chloride ion, so I would be 3. However, if I had something like aluminum chloride, you actually get 1 aluminum and 3 chloride ions, so that sums to 4 particles for every 1 aluminum chloride. And then be on the lookout for anything that's molecular. For example, glucose, C6H12O6. That would have a Van 't Hoff factor of just 1, because glucose doesn't dissociate. You get 1 glucose particle for every glucose molecule. So the I factor is really just something you have to look out for ionic things that dissolve. Okay, so that's how we can calculate freezing and boiling point changes. Before we practice that, I'll show you one other colligative property that's called osmotic pressure. And let me first explain what that is. Osmotic pressure is the pressure needed to stop osmosis. And that means we should really say, what's osmosis? So you might remember from your biology class that that's the flow through a membrane semi-permeable membrane from high concentration to low concentration. And we see this in biological systems, but you can simulate it in a laboratory setup with something that looks like this. Here is what looks like just a beaker of water, and then there's a flask with some solution submerged. And what I have in this diagram is a membrane that separates that flask from the surrounding water. So a semi-permeable membrane means that small molecules like water can migrate back and forth through that membrane, whereas the solute has to stay put. And osmosis is the movement of water molecules from an area of high concentration, meaning the pure water outside, into an area of low concentration of water. So there's going to be a net flow of water into this solution as a result. And you're going to slowly see a liquid level rise, as they show in this picture, until you get to a height difference that's just overcoming the force of gravity. And when you hit that point, that's called the osmotic pressure. So there's a driving force for water to go in that's based on the concentration gradient between the two, and water will continue to do that from that driving force until it can't overcome that height pressure difference any longer. That's called the osmotic pressure. And we can quantify this. It's abbreviated pi. It's based on the Van 't Hoff factor, the particles of that solvent, and just the molarity of the solution, as well as the ideal gas constant and the temperature. So pi is what we use to abbreviate osmotic pressure. I is still the Van 't Hoff factor, M is molarity, R is the ideal gas constant, 0.08206 liters, atmospheres per mole Kelvin, which obviously means T is in a Kelvin temperature and M is a molarity. So those are the 3 equations that we see for calculating changes in freezing and boiling points and osmotic pressure. Now let's just wrap up and practice using them. I'll do the first batch and then let you do the rest. So the first one says, what's the molar mass of glucose, a covalent substance, if 18 grams of it dissolve in 100 grams of water and the solution boils at 100.34. So this is a delta T equation. Delta T B is equal to I, K, molality. The delta T is how much higher it boils, so it's only 0.34. I, it's molecular. It says it's a covalent compound, so I is 1. KB is 0.512. And the molality actually has a lot of stuff in it. Molality, if you remember, is moles per kilogram, which is mass over molar mass, and then still times kilogram. So our unknown molar mass is buried inside that molality. So I'm going to substitute m over mmkg for this molality, where our mass is 18 grams, our molar mass is the unknown, and then the kilograms of solvent is 0.15 because it says we have 150 grams of the solvent. And then you just rearrange and solve for molar mass, and you get 180 grams per mole. And that should come as no surprise if you remember what the formula for glucose is. It's C6H12O6, which adds up to 180. So using changes in boiling point can be a way of solving for the molar mass. Let's try another one, just an example. Here we want the mass of the solute. This is ethylene glycol. They give us the molecular formula. They tell us there's 10 kilograms of water and it freezes at minus 10 Fahrenheit. Fahrenheit. The first thing I need to do is convert that. Well, remember, a Celsius temperature is a Fahrenheit temperature minus 32, and then times 5/9. If you plug in negative 10, you get about negative 23.3 degrees Celsius. So that's our delta T right there. So delta T is equal to I K M. Delta T absolute value is 23.3. I is 1. This is freezing point, and it's water, so it's 1.86. And then once again, the mass is buried inside the molality. So molality is moles per kilogram, which is mass over molar mass times kilogram of solvent. So there's our unknown, and I substitute that here, m over the molar mass. 2 carbons plus 6 hydrogens plus 2 oxygens gives me a molar mass of 62. And then kilograms of solvent will be 10. So I just rearrange and solve for m. You get a very large 7,770 grams per mole. And that's really a testament to something, not grams per mole, just grams. Just grams. It's a mass. And that is a testament to actually how much solute it takes to get a significant change in freezing point or boiling point. Even though these things are measurable, usually the changes in freezing and boiling point are very small for a solution. That's actually why we have osmotic pressure. I'll skip a few and look at number 19. And see if we can solve for the molar mass based on an osmotic pressure. Osmotic pressure differences are actually much easier to measure. They're more significant. Even though this is only 1 torr, we can measure that more easily than a decimal of a temperature change. So osmotic pressure is pi is equal to I, M, R, and T. Pi is 1.12, but that's in torr. I need to make that into atmospheres, so take 1.12 and divide it by 760. I, if I read the question, this is a molecular substance, so I is 1. The molarity is the moles over the volume. I have a mass and a volume, so I'm going to extract the molarity into what it really is. It's my mass, 1.00 milligrams divided by a molar mass, and the volume is 1.00 milliliters. You might be going, wait a minute, that's milligrams and that's milliliters. Shouldn't we turn this into grams and shouldn't we turn this into liters? Yes, but think a little bit more smart. There's milli and milli, and those cancel. So milligram per milliliter is the same as gram per liter. So I could just leave these as 1 and 1, and I get a molar mass in gram per mole, or milligram per millimole, which is the same thing as gram per mole. So I'm just going to leave it as is. R is 0.08206, and T, 25 Celsius, that's 298 Kelvin. So I rearrange and solve, and you get a pretty big molar mass of 16,600 grams per mole. And I think not the solutions, but the answers are actually at the bottom, so you can check if you're doing these things correctly along the way. And indeed, that's right. That might look a little bit strange at first. Isn't that a huge molar mass? Yes, it is, but remember, this is a protein. Proteins have big molar masses, so that makes sense. And you could use very little of that protein to get a measurable osmotic pressure change. Okay, that's 3 of them. There's 3 more that have to do with delta T's and osmotic pressures. I'd like you to hit pause and see if you could do the remaining 3 questions and then come back and check and see how you did. Okay, well, number 18, welcome back. This is a freezing point change equation, I can tell. So delta T is IKM. The delta T is 0.24. This is molecular, 1. K, ooh, it's a different solvent. I have to use the given K value, 5.12. The molarity, the molality has mass buried inside of it. It's an unknown molar mass, but a known mass of 0.546 grams divided by an unknown molar mass times 0.015 kilograms of the solvent. Don't forget to convert that into kilograms. And when you solve for the molar mass, you get 777 grams per mole for whatever this substance is. Interestingly, you get a much bigger freezing point change for benzene than we do for water. This is like an order of magnitude bigger. The K value really depends on what the solvent is. Going over to number 20, this is an osmotic pressure problem. So pi is IMRT. They give us the pi at 7.7. It's sodium chloride, so I is 2. The molarity is our unknown. R is 0.08, 206. T is 298. You plug in and solve for molarity, 7.7, divide by 2, divide by 0.08, 206, and 298, and I get 0.157 molar. That one was a little easier. We just had to solve for the molarity. They're not making us extract a molar mass or a mass or anything. The last one, 21, might have been the most confusing. It's an osmotic pressure equation. Pi is IMRT, and they tell us that pi is 10.8 atmospheres, but they want us to solve for I. So if M is 0.10, R is 0.08, 206, and T is 298. I'm leaving my units out of the work here, but you really shouldn't, unless you're really comfortable with what you're plugging in here just for your own work. But for communicating it to others, you should really put your units in the work. It's much clearer when you do. Definitely put them in the answer at the end, although I is unitless. When you do this, you get a value of 4.4 for the Van't Hoff factor, which is not a whole number, and we haven't seen that before, but we can actually make sense of this. So what does this mean? Well, the solute is an iron complex with 2 ammonium ions and 2 sulfate ions. And at first you might go 1 iron plus 2 ammoniums and 2 sulfates. Isn't I going to be 5? Well, no, it's apparently not. So this thing forms what are called ion pairs, which means it doesn't fully dissociate. And we would not have known that if we didn't make a solution out of it and experimentally determine the Van't Hoff factor. This is actually one way you can figure out how much an ionic substance dissociates. It's a safe assumption that ionic substances that are soluble will dissociate completely, and we can usually assume that. But in rare cases, especially at higher concentrations, it doesn't dissociate fully. We actually get a number that makes sense. It's less than 5, so not all of them dissociate into complete particles. That's really all that means. And it's a sneak preview of what you might see in college chemistry, which is that some of the things we learn in this high school class don't completely apply to more concentrated solutions. You'll learn more about that when you go into college-level chemistry classes. Okay, so that wraps up the solutions unit, talking about how solute concentrations affect freezing point changes, boiling point changes, as osmotic pressure changes, and how we can use these properties of solutions to find things like the molar mass of various solutes.